Okay, it's Wednesday, the 17th of February. We're going through go through our last set of notes on chapter 22. Uh, we're going to get into what's called the electric field. And we're going to be covering this a lot more in the next few chapters, and this will lead into concepts called electric potential differences, voltages and currents, and all of the electronic stuff that we're going to do later. So we're just going to briefly get started on this today in the last part of chapter 22. In all honesty, I don't know why the author doesn't just put this in a separate chapter and start it then, but anyway. So let's start off with a quick review of electrostatics and Coulomb's law. So remember yesterday we discussed that we can calculate the force if I have two charges, Q1 and Q2, and these are the net charges on each body. And if they're separated by some distance r, that we can use Coulomb's law to calculate the magnitude of the force. Remember, we don't put the signs in, just the magnitudes of Q1 and Q2. And if r is their separation, we can get the magnitude of the force acting on the two bodies. And then remember, we draw whether it's attractive or repulsive determines the direction of the force. It's always along the line of the two charges. So we can use Coulomb's law to calculate the magnitude of the force, and we use direction as from attraction or repulsion. Here's an example. If you have two charges that are the same sign, they will be repelled, and so the forces will be opposite one another, but still along the line of sight, but along the line joining them, sorry. And if you have two charges that are the opposite signs, they attract, and so the forces will be trying to pull them together, the electrostatic forces. So we get the magnitude from Coulomb's law, and we determine based on their signs the direction of the force. Yesterday we went into Coulomb's law, and if you have more than two charges acting on another charge, we simply add the vectors for each force individually, and we sum the vectors up to get the total magnitude and direction of the resultant force. And that's called a principle of superposition. So that allows us to calculate the net force if there's multiple charges, each exerting forces on some other charge or on each other. We're going to get into this concept of the electric field, but before we do that, you've already done some of this. So I want to bring back an analogy to gravitational forces and fields because they're so similar. So let's start off with something you're familiar with. So at the end of Physics 1, you should have discuss Newton's universal law of gravitation, right? If you have two masses, and one of them has a mass big M and the other has a mass little m, and they're separated by some distance r, that Newton's law of gravitation allows us to calculate the gravitational force acting between the two bodies, right? And they're equal in magnitude and opposite in direction. So they attract each other with the same magnitude of a force. And that negative sign means that it's always attractive. The force is always pointing along the lines between the two masses. Now, if you look at Coulomb's law, the equation is almost identical, except for here you have charges playing the role of masses. So the forces between two charges, Q1 and Q2, separated by some distance r, is given by Coulomb's law. And here, instead of big M times little m, the product of the masses, we have the product of the charges. The magnitude of both of them is separate, depends on the square of the distance, and then they each have a different constant. And so the equations for the Coulomb force and the gravitational force are almost identical except for the sign. And gravitational force, the force will always be attractive. It'll always point toward one another, the masses. Only with Coulomb's law, it will either point toward one another if they're attracted to one another, if they're the opposite charge, and if they're the same charge, it will point in the opposite direction. So with Coulomb's law, it can either be attractive or repulsive. With the gravitational force, it's attractive. But other than that, these equations have identical forms. It's just charges playing the role that masses played with the gravitational force. And so, since these equations are virtually identical except for the sign, we can use a similar concept used for a gravitational study of gravitational forces to describe electrical effects. When you discuss the gravitational forces, and if you just look at the magnitude, it's G times M times little m over R squared. You often wrote this in in physics 1 as the gravitational force is little m times G. Remember, where G was 9.8 times 10 to the negative, 9.8 meters per second square is the gravitational field strength. So what was this little g? Well, this little g, if you're talking about the gravitational force acting on a body due to the Earth, so in this case, big M is the Earth mass, little m is the mass of some body moving in the gravitational field of the Earth, and r is the distance from the center of the Earth to the surface, in this case. And you plug in numbers for G. Big G is 6.67 times 10 to the negative 11. You plug in the mass of the Earth. You plug in the radius of the Earth. And we got that little g was 9.8 times 10, 9.80 meters per second square if a body is moving close to the Earth's surface. In other words, if you're close to the Earth's surface or you're not too high up, this distance r is roughly the radius of the Earth. It's so much larger than the elevation. As long as we're not too far above the surface of the Earth, little g is about 9.8 times 10, 9.8 meters per second square. And so in this case, we wrote that the gravitational force is just little m times this gravitational field strength. And this is kind of nice because suppose that at each distance, if here's the mass of the Earth, and here is the center of the Earth, and at each distance above the surface, that's a little bit different, little bit different distance of r, we calculated the gravitational field strength little g. And suppose we calculated this at all points. We can add a vector, we can use at each point, we can draw a vector whose magnitude is little g and whose direction points toward the center of the Earth. And this is what's called the gravitational field. And to calculate the gravitational force on a body at little mass m at any distance, suppose it's orbiting the Earth at some low orbit, all we need to do is find the gravitational strength little g at that location and multiply it by the mass. So if we can make this is a gravitational field, so at each point is a vector representing the magnitude of the gravitational field strength and the direction pointing toward the center, then the force any mass m experiences is just m times g. And this little g depends only on the mass of the Earth and on the position. It doesn't depend on the mass of the body that's interacting with the Earth. And so this is the concept of a gravitational field. It's the force per unit mass. Little g is the force per unit mass at a distance r from the center of the Earth. Okay. So the key point here is that we can describe a gravitational force acting on any mass simply by calculating the Earth's gravitational field strength, little g, at any altitude, and then multiplying it by mg. Okay. We can do a similar concept for the electrical force if we define this quantity called the electric field, and we're going to denote that with a big E. And this plays the same role as little g did with gravitation. It describes the effect of the electric force due to a distribution of source charges. And if we know the electric field strength at any location, we simply multiply it by Q to get the total force acting on it. So let's get into this here. So we're defining the electric field because it's often easier to discuss electrical interactions in terms of electric fields instead of electric forces. Another reason is we can measure the electric field strength. Okay, so it's a lot easier to deal with fields in practical situations, especially like in chemistry, you're dealing with electric fields produced by charges. If we're dealing with TV antennas, if we're dealing with forces on charged particles in tubes, it's often easier to deal with electric fields instead of forces. So what this field is, by definition, at some point P in space, the electric field is the force that would be exerted on some positive test charge, Q0, due to all of the other source charges. Okay? So what we mean by this is that we're going to take this little probe charge Q0 and we're going to stick it at some point in space and we're going to calculate the force on it due to all of the other charges. Then we're going to divide by Q0, and that's what's called the electric field strength. So let's do this here. And since F is the force acting on this charge, and Q0 is the charge itself, the electric field has units of newtons per coulomb. And so what this means is it answers the question, how many newtons of force are exerted on each 1 coulomb of test charge placed at a given location in the electric field. So let's do an example here, and we'll go back to our hydrogen atom. And so remember, a hydrogen atom, there's a nucleus, and the nucleus is just a proton with a charge 1.6 times 10 to the negative 19 coulombs. So let's calculate the force that would be exerted on some positive test charge of 1 microcoulomb placed 0.53 angstrom, where 10 angstrom is 10 to the negative 10 meters from the nucleus. So in other words, we're going to stick a little probe at 0.53 angstroms away from the nucleus. We're going to calculate the force exerted on it, and then we're going to divide by this Q0, and that's the force per coulomb exerted on a particle at that point due to the hydrogen nucleus. Okay, so let's do that. So we apply Coulomb's law, where Q1 is the charge of the nucleus, which is 1.6 times 10 to the negative 19 coulombs. And Q2 is the charge of our little test probe here. So suppose we stick a 1 microcoulomb test probe at this distance from the nucleus to measure the force. Okay? And we plug in the numbers, and we get that the force exerted on this test charge is 5.13 times 10 to the 5 newtons. The test charge is positive. The nucleus is positive, so it points radially outward away from the nucleus. So that's the force on the charge. Now the electric field is the force divided by the charge, Q0, and we're dividing it by the charge, 1.0 times 10 to the negative 6 coulombs. And what that means is that the electric field strength is 0.513 newtons per coulomb. So what that means is that this proton will exert a force of 0.513 newtons on every 1 coulomb of charge placed at this distance from the nucleus. Okay, so if we place 2 coulombs of charge at this distance, it would be 0.513 newtons per coulomb times 2 coulombs. That 2 coulomb charge would experience a force of 1.026 newtons. And if we place 3 coulombs of charge at that location, it would experience a force 3 times 0.513 is 1.5 newtons. So the nice thing about this is once we know the strength of the electric field, we put any magnitude charge at that location, we just multiply the electric field strength by the magnitude of the charge, and we can get the force. Okay, and so the magnitude of the force at this average distance of 0.53 angstroms from the proton is 0.513 newtons per coulomb. Okay, so if you placed we would place the electric field, we would draw the electric field as a radial line going outward because it's repelling the positive test charge. Okay, and so the electric field, since by definition the test charge of our little probe here is always positive, the electric field produced by a proton or a positive point charge will always point radially outward. Okay, and if you look, I could place this test probe charge Q0, I could place it anywhere along this circle at the same distance, and the electric field strength would be the same magnitude, and it would point radially outward. So to calculate the magnitude of the force, I can get the electric field strength and multiply it by Q0. So what happens if I stick an electron at this location? Okay, well, the electric field's in the positive direction because electric field by definition is the force on a positive probe charge. If I stick an electron here, the electron will be attracted. So the magnitude of the force is the same, but the force would be toward the proton. Okay, so the force produced on a negative charge particle in this electric field is opposite the direction of the field. So the one nice thing about this is you saw from this first example that it doesn't matter what magnitude this probe charge is. We could have put 1.0 times 10 to the negative 12 coulombs, or 1.0 times 10 to the negative 15, or 1.0 times 10 to the negative 18. It doesn't matter because you're going to divide out by that number anyway to get the electric field. Okay, so it's independent of the size of the probe charge. Okay, so to calculate again the electric field, we put a probe charge at some distance r from the source. We calculate the force acting on the probe, Q2, due to the source charge, Q1. We divide by the square of the distance and we get the force. Then after we get the force, we divide by the size of the probe charge, Q0, and we get the magnitude of the electric field. And if we go to some other distance r, we do the same thing, and you're going to get a different electric field strength. And suppose that at any distance r from the source, we did this calculation, we would then have a map of the electric field strength at any location due to this source charge. Okay, so that's how we calculate the electric field. Now, once we know the electric field strength, suppose we want to know the force, well, then we just multiply the force, the electric field, by Q, which is the charge that's at that location. We get the force, we can set F equals ma, and we can determine the acceleration of the charge. And so as we move on in our studies of electricity and magnetism, we're going to start moving away from thinking of forces and start thinking more of electric fields produced by the sources instead of F. Okay. So we could do the same thing if we placed a negative source charge, and at this distance we put a positive probe charge to calculate the field. The positive probe charge will always be attracted to the negative charge, and so the electric field would always point toward a negative source charge because the positive probe charge would be attracted at any distance. If we have a positive source charge and we stick our little positive probe anywhere, it'll always be repelled. And so the electric field lines always, these vectors always point away from positive charges, and the electric field lines always point toward negative source charges. So again, this is the importance, is that when we get past this chapter, we're going to be discussing electrical effects in terms of the electric fields instead of electric forces, just like we discussed gravitational forces in terms of the gravitational field, little g is the strength, instead of using Newton's law of gravitation for many calculations near the Earth. So to calculate the electric field, we move our little probe to every possible location. We calculate the force on our positive probe charge due to this plus source charge here. We know that it's repulsion because the positive probe is repelled. And so we get a magnitude and a direction of our vector of the electric field at every point in space. Then we can go on to point 8, point 7, point 6, and we can assign vectors whose direction is the direction of the field and the length is the magnitude of the electric field at each location. And so every point in space is assigned a vector which tells us the magnitude and the direction of the electric field produced by this positive charge. Okay? And again, if you have a negative charge here, you would still have the same magnitude of the field, but the direction would be pointing toward the source charge because the positive probe charge would be attracted to the negative charge. And so that's pretty much it right now for our first chapter. That's about as far as we're going to go with this intro to electric fields. And we're going to get into more detail next week in chapter 23 after your exam on Monday. So this concludes chapter 23, and this concludes our lectures for this week. All of the lectures are on As You Learn, the PowerPoint notes, and we will see you next week after your exam.